So in this video, I wanted to talk a little bit about magnetic torque, magnetic energy, and magnetic moments, and how that relates to a practical application, MRI. All right, and so I'm following along with my book on page, approximately page 218 in my book, where I'm talking a little bit about magnetism and quantum numbers. All right, and so the scope of this course is not to learn quantum numbers. You can learn about that in chemistry, but maybe you've heard of them, like there's N for the energy level. And then there's L for angular momentum. These are what the quantum numbers stand for in chemistry. Then there's M sub L and M sub S. Now, related to all that, this is like orbital, whoops. Let me get the right term. Well, let's just, so they call this one the magnetic quantum number. All right, interesting. Right, and the last one is going to be the spin quantum number. There we go. All right, in this case, this one is the Z component of the electron orbit and the magnetic moment associated, or the Z component of the angular momentum. And this is related to this new quantity called spin. What I'm about to talk about gives you a physical understanding of it, but it is not, like I said, I'm glossing this over dramatically. You'll learn about it in another class. But you could imagine if you had a charge spinning, right? Imagine if you just took a beach ball and covered it with fur and spin it. You could imagine, and rubbed it with fur so it was covered with charge and then spin it. You could imagine you'd have charges going in a circle. It would look a little bit like a current loop. That is not what spin is. Okay, spin is not a charged billiard ball spinning, and right, but phenomenologically, it's a little bit like that. So for now, just imagine you have an electron here, or you could have a proton in the nucleus, right, spinning. So you have some sort of atomic particle and it's spinning. Well, you could imagine, let's say we have an electron here that's spinning this way. All right, so again, this would correspond to an electron that's just spinning this way. If that is the case, what direction is the magnetic moment? You can pause the video and take a second to think. We have an electron that's going this way, like that. What direction is the magnetic moment? All right, so if you had a chance to take your guess, remember that the current flow would actually be going the opposite way. So this would be current, and this would be electron velocity. Right, so if the velocity is going this way, that's equivalent to a current flowing this way, right? And maybe that's super terrible to describe it that way. Whatever, I just wanted to remind you that current flows opposite of direction flow. So if this one's going this way, the magnetic moment might be off in this direction here. Now, the easiest thing that helps me understand these equations is the following. I know magnets like to be aligned with each other, so their north poles are facing the same way, right? So if my north pole clicks into the south pole, notice the north poles are both pointing the same way. So these two equations up here also help us understand that mathematically, right? It's energetically favorable for a magnetic moment to be aligned, right? If mu dot B, if they point the same way, this is a positive number. The negative sign gives me a very negative energy, a very low energy. If they're anti-aligned, I would get a negative number for the dot product, and I would get a very large positive energy. So it's less energy for them to both point the same way than it is for them to point opposite ways. A weird side effect is there's zero energy if they're perpendicular, right? But that, yeah, remember, it's sort of like you could set your height level at 0 in the middle of the problem too. And that's what's basically being done here. We're calling the middle of the problem 0. This would be high energy, zero energy, negative energy. All right. Similarly, we get this torque equation. All right. So mu cross B. First goes to second. Notice I get a torque into the page that's going to rotate. Either way you look at it, if this is my external field and this is my magnetic moment, they want to align, right? So there's going to be this tendency of this magnetic moment to pop up this way, right? That's evidenced by the direction of the torque being into the page. It wants to curl up, or it's evidenced by the energy, right? It would be less energy to snap to this spot. Now it may have to give off some energy, right? If this wants to snap to that location, right? There's a change in energy. If you change the energy, maybe you could emit a photon, all right? So, and that photon might have energy. So you're going to see me write E subscript gamma for the energy of photon. That's light, right? So there's some energy associated with the light that leaves. Now, as we'll learn soon enough, the energy of a photon corresponds to its frequency and a constant. So the energy of a photon is directly proportional to its frequency. This is some constant. Okay, that's Planck's constant. All right, so I'd have to look up the number. It's on the back of my book so I don't screw it up. All right, 6.626 times 10 to the minus 34, I believe. Making sure I get the power right. Yes, joule seconds. All right, so great. Interestingly enough, we see that the magnetic energy could possibly relate to photon energy. So far, so good. Now, in this case, I want to actually go to a simulation here. And let me see if I can share screen. All right. Now, in this case, I'm going to turn off this magnetic field here. Right now, there's no magnetic field present, and we just have a bunch of atoms here. To be clear, we're actually looking, I believe, at the nucleus. So in this example, the arrows inside of here, all these little red arrows pointing this way or that way, are corresponding to the spin magnetic moment. So this is something like the mu associated with spin of the nuclei, right? So we're looking, basically, you could think of this, if we're doing hydrogen, we're thinking of this as basically the proton spin, right? So that's the mu associated with the spin of the nuclei. All right, so far so good. Now what I'm going to do is I'm going to turn on a magnetic field. As I turn on the magnetic field, keep an eye on this section of the graph that I just annotated over here. When I turn on the magnetic field, we should see the energy change a little bit. So let's do that. Whoops. As I turn on the magnetic field, right, we see a high energy and a low energy. And we see that some of the atoms are in some state and some of the atoms are, or some of the nuclei are in one state. The idea is there's a low energy, which corresponds to being aligned with the magnetic field. So maybe I'll write aligned here. And there's a high energy state when the Z component mu sub, when mu is anti-aligned. Now you may be saying, how come some of them go up into that higher level? Well, they have some thermal energy, right? There's energy that they have. Perhaps there's been collisions and all kinds of different things. For any number of reasons, you could have a few protons in there that have some energy. And that's why there's always some in the anti-aligned state. And now what I'm going to do is I'm going to send in some photons, all right? And what I'm going to do is if I send in photons, I'm hoping I could tune this system. Now in this case, I want you to keep an eye on this right here. The idea is that corresponds to the energy of the photon that we were just talking about. The energy of the photon is proportional to the frequency. Okay, so if I get the frequency just right, I'll have photons coming in that have just enough energy to kick up these low liars up into the higher energy state. Let's see what happens if I do that one. All right, so And let me just get rid of that line. So what I'm going to try and do is adjust the frequency. Now it's just matching. And watch what happens. We're seeing this population invert. Now it's actually more common to be in the high energy state. The idea here is every time you get a proton in the low energy state, a photon comes in, and notice, if I could pause this here, at 1 second in time, I just want to point out B external are these arrows, right? B external. And notice, look at all the protons in there. See how all the red lines on these, they're all pointing down right now. They're all anti-aligned. And that's because they just absorbed a photon that gave them just enough energy to flip to the anti-aligned state. Now, what's up with these photons? Do you see how there's some photons coming up and leaving the side, right? The idea is that we're sending in energy this way, but then when these protons relax to the low energy state, they send out photons in all directions. Now we're only seeing some of them being emitted, but the idea is when these protons relax, they're going to send them out in every direction, not just the direction that the energy came from. To make this a little bit easier to see, let's run this a different way. What I'm going to do is I'm going to send in a wave. All right. And so now we can see there's a wave of input energy coming this way. So this is the energy input. And we see these are radio waves coming out that could be detected. And here we see the cool part about this, right? What happens here is you can send in radio energy in one direction, and if a proton absorbs it, it will later re-emit it out a different direction. So you could put a detector perpendicular to the direction. So you could put a detector over here. You could put in some pickup coils. And what would happen is you could detect the radiation that's emitted by these without having to pick up the radio signal you send in yourself. All right, so that's one key issue here. We see that the radiation re-emitted by these protons as they relax down to the low energy state can be emitted perpendicular to the incident energy. Now, the other interesting thing is if I up the magnetic field strength, we should rapidly see this thing fall apart, right? Now there's not any up in the high energy state. So notice if I use more magnetic field, I'm going to have to use a different radio frequency. Aha. So we see that different size magnetic fields will communicate with different radio frequencies. Got it. Now let's go to this page. And I just think this is so interesting. And I know this is simplified, but please, I hope you find this cool. What we can do now is we could take this magnetic field and I could put a gradient on it. Now notice there's different B externals pretty much at every point. Here there's B external is approximately 0. And here B external is large. Let's just say it's 10 or something, right? Or whatever. I guess it will probably be about 0.85, I believe. Something like that. But again, I'm not, whatever. It's a big number. It's not exactly just this plus these two numbers, right? Because one's horizontal and one's vertical. But all right. In this case, the fact remains is the B field is different at pretty much every spot in here. What does that mean? It means there's a frequency that corresponds to each different spot in there. So what we can do is we can send in different frequency radio waves and communicate with different parts of the body based on the frequency I choose. If I choose a super low frequency, I should be communicating with protons in the low B field region. Now, there's always going to be some random thermal excitations. But so notice we could see maybe what I could do. Oh, let's go to the photon view for a second, right? We're sending in all these photons, but they're pretty much only interacting in the low field region, oops, right up in here, right? So we're seeing this action, this particular proton is reacting to that radio frequency. All right, so let's go back to radio wave view. All right, if I go to a slightly higher frequency, let's see if we get different parts of this responding. Now I'm seeing more different things responding over in the bottom right. If I keep going up, we're probably going to get down to where only the bottom right starts to interact. And so different parts of the body are reacting to different radio frequencies because there's a strong field with a gradient, right? There's a changing, the field is different at different locations. And the idea is, in theory, you could use this to identify a tumor. You could sweep the frequency, right? And you could actually look inside the body and notice, there's a lot of extra protons interacting with a radio field here that shouldn't be there. Maybe we should check that out. All right, and anyways, I know this is super simple. I'm going to send you some other videos that kind of show you more about the relaxation process and going from the upstate to the downstate. But that's a super simple version of the MRI, and hopefully that was kind of interesting. So let's go ahead and call that a video.